Okay, now let's analyze Bernoulli's equation. The problem is this. We know that y2 is higher up than y1, so we can say that y2 in this case is greater than y1. We don't know what the velocity at v2 is, or what the velocity at v1 is, and that means that we can't relate the pressure at the second position to the pressure at the first position. So we don't know if the pressure is greater or less when the area is wider. In order to find that out, we've got to find out something about the velocity. Because gravity is a constant, density is a constant. So we have three variables that are unknown. We have pressure, velocity, and the height. The height is easy to determine. y2 is greater than y1. Now we need to say something about the velocity. In order to understand the velocity, we have to understand the mass flow rate. The mass flow rate is the change in mass over the change in time. Now, mass has a density relationship. Density is mass divided by volume. So mass is equal to density times volume. So we set that equal to this. Density times the change in volume is over the change in time. That's equal to delta M over delta T. Now the change in volume is equal to the area times the change in length. So we have density times area times the change in length over the change in time. Now velocity, the basic definition for velocity is distance over time. And in this situation we have a delta L over delta T. So we can make a substitution here and say this is rho A V. Because delta L over delta T is velocity. Now we have a relationship for velocity. We need to do this. If we have the change in mass of 1 over time is equal to the change in mass of 2 over that same period of time, we can relate the velocity of 1 to the velocity at point 2. And we end up with rho A1 V1 is equal to rho A2 V2. By that same derivation, just applying the subscripts 1 and 2 to the different situations. Now, densities cancel out, so you're left with area 1, velocity 1 being equal to area 2, velocity 2. Let's just get velocity 1 by itself and see how velocity 1 compares to velocity 2. So we divide A1 to the other side, you get A2 divided by A1 times V2. Now we can analyze this. A2, coming over here, A2 is going to be a small number, A1 is going to be a larger number. So what we're going to do is just look at the equation. We'll have A2 is a small number, A1 is a large number, and that's V2 equal to V1. Now, if you take a small number and divide it by a large number, you're going to get a small number. Let's use a decimal point. Let's just use 1 over 10. V2 is equal to V1, and that's 1/10. V1 is equal to 0.1 V2. This means that you're going to get V1 is equal to 1/10 of V2. So V1 is smaller than V2. If the velocity at point 1 is less than the velocity at point 2, then we can now form a relationship between the two pressures. So we go back to Bernoulli's equation. Velocity 1 is less than velocity 2. We look underneath here. Y2 is greater, V2 is greater, V1 is less than, and Y1 is less than. What this means is that in order for this side to be equal to that side, the pressures have to be different. So if your velocity and your height are greater, that means your pressure has to be less. So P2 has to be less than P1. And going back over here to the diagram, pressure 2, the pressure of the fluid flowing out of the thinner pipe has to be less than the pressure, P1, that flows in the thicker part of the pipe. That means it has to be moving faster. So you have a smaller pressure when you go from a large pipe to a small pipe, a smaller pressure at the top, larger pressure at the bottom. And that's how we can basically analyze Bernoulli's equation for the three variables of pressure, velocity, and height.